The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Alright, so we're team M3. Our job was to optimize the roller assembly of the climber and make it basically the main part that we were optimizing was mass, but we were also optimizing the time to put it onto the ribbon and the cost of the climber. We decided to set the material as polycarbonate though, so we didn't do a case study for different materials. So, as I just said, the motivation for working on this term was to make it so that we needed less power in order to climb up the ribbon, which would therefore increase the score. Scoring metric being the speed of the climber times the payload mass divided by the total climber weight. So basically, the roller assembly, which you see right here, is what rolls up, which is what is used to climb up the ribbon. And we put the power system, which is yet to be completely defined, just below it to get the power transferred to the motors. So basically, what we decided to do was that we were going to optimize for this IAP the side plates that you see here, or the side bars, the side plates, and the rollers. Because as you can see, especially on here, that the side, especially these rollers here, have a lot of extra mass that is not necessary. So the requirements that we have for this are to minimize the climber weight, the cost, and minimize the time to attach the climber to the ribbon. Based upon the amount of time that we're given at the competition, we decided that a reasonable time would be about 4 minutes to basically take these two sides, put them onto the ribbon, and clamp them. And to maintain a von Mises factor of safety of at least 2, which we'll go into a little bit later once I show you the finite element analysis. The constraints that we were left with in order to do this were to allow the climber to survive a 2-meter drop test. Basically, this was something that was laid out in the competition rules that the climber must be able to withstand. Also, that the climber must lift its own weight. Obviously, if it cannot lift its own weight at least 2 meters per second, then we're not going to meet the competition goals. And the material must be unaffected by 5.8 gigahertz microwaves, since that is our current idea of how we're going to bring power up to the climber. Also, climber must be unaffected by water in the case of rain or any other such things, and be able to resist 11.5 mile per hour winds, which was a really big problem for people at the competition last year. So, to start out, we came up with some initial sketches of how we were going to take off weight. Basically, these were just a very first iteration guess as to what it was that where we thought we could take off mass and for it to not matter. So we just kind of, what you see here are the holes where the axles go in. So these were defined, as were these for the locations of the sidebars. So those are all defined, so we couldn't touch that. So we basically just put in weight reduction holes and basically all the other places. For the rollers, basically what we did was we took a design that we were using in our first iteration and had little caps on the rollers. And here's just a top-down view. So the caps would go here and here, and then we have a tube in between. And you'll see that a little bit better later on when we show you the CAD models. And for the sidebars, we just made like a truss structure. So the design choice was basically that the initial design was given to us right here, and we were just going to take off weight where it was possible, and place the host in strategic locations, and then we will refine it with finite element shortly. So we're left with the side plates. Here's the final CAD models after we've optimized them. So one thing to notice is that these look a lot different than that sketch beforehand. So we noticed that these are not good locations to put the holes.
3 minutes of video missing due to technical difficulties. Here are slides from the missing video.
We punch the numbers into SolidWorks and choose the English metric, then try to convert it ourselves and maybe forgetting. So, and then we also have the axle force, basically just the force that the rollers are taking. And we calculated that force by taking the force that is necessary to pull the climber up, which is 123 newtons, the weight of the climber, and dividing it by 2, by assuming that each vertical position on the roller would need to take half of the force. And we restrained it at the sidebar locations and put an additional force at the bottom of the equivalent of 15 kilograms, except for weight. And here you can see the factor of safety diagram. Basically, most of the problems here still have a bit of dead weight, but there's not much that we could really do about that because of the locations of these holes. And the displacement, the maximum displacement, -5 or so meters. So even though this looks really constrained, it's very magnified. This is also towards the bottom, so that's why we have like this mass here. So for the sidebars, a little bit clearer, we basically put the force, the outward force and downward force coming off of the motor and restraining it here, and left with a factor of safety about 2.2, which is just above what we set our minimum to be, which is just about right. And the displacement, this is perfectly reasonable for what we're talking about right here. And you can also see that a lot clearer than in the side plates. This is much more optimized in that we're spreading the force much more evenly along these bars. And if we were to pump up the coloring a little bit more, you'd see this is actually much more distributed. And same idea for the Belay forces, that we have this very evenly distributed, and displacement again a little bit larger, but for the case of having to be pulled up in this direction, that's really nothing to worry about. And for the drive rollers, basically we took the force, like I said before, divided the force that was needed to pull the climber up, divided by 2, and applied that in the form of torque to the rollers. Basically, since there's no other way to easily apply forces along the whole surface of the rollers, so we decided to use torque, and that provided much better results. And what I was saying before about the width of the caps, that was determined by basically, as you can see the red down here. As soon as I got that to be about 2.1, then I stopped increasing the cap width. Then once I realized that the caps were very thick, then I hollowed them out and realized that made absolutely no difference in the factor of safety, or the displacement for that matter. Same idea for the guide rollers, really no difference, 2.1, a little less displacement. So, for the parts that we actually machine, we put a few parts into the water jet and actually machine those. Here you can see the Belays. Basically, as I showed before, these are the ones that go on the top. And we popped them in the climber, but for the initial test, we did not want to use them just because they would potentially be accepting a little bit more stress. So I will pass these around. And those ones have already been milled out. All the holes are in, so they're basically good to go for being placed onto the climber. As for the sidebar, though, this has not been milled out. As you can see, it does not have the roller holes in it because we wanted to wait for the other plates to be able to be water jetted out before we could do that. So, pass that around too.
Yeah. Some of these edges look a little rough.
Yeah.
You know why that is?
So basically, on the side plates especially, we didn't really do all that much filing down. We used a quality of 3 on the water jet, and we're also thinking we're probably going to use a higher quality next time. With aluminum, quality of 3 is fine, but with polycarbonate, based on the way it interacts with the water, the jet of water, apparently it's not quite as happy with the quality of 3. So, pass on to Carolyn.
Okay, so these are the final specifications that we figured out using SolidWorks. So we had our 4 requirements essentially that we wanted to optimize as much as we could for our climber. This is our final CAD drawing. As you can see, the holes are located. These are the capped rollers and new sidebars and Belay sidebars are in place. So this is hopefully what our assembly will look like once we're finished machining all the other parts. And our main requirement, our main focus in all of this was to minimize the weight, as Ryan said, so that our climber will go faster and that we can maximize our score as much as possible. So originally, the weight for the sidebars were 0.124 pounds, which is not that much, but we managed to decrease it to 0.051 pounds. So that was a pretty significant difference, a very nice drop there, and especially since we have many sidebars, it's nice to have that weight incrementally decreased. We also managed to drop the sidebar belay weight by almost the same amount. Admittedly, there are only 2 of those, but once again, each little bit adds up. The side plates. The left side plate was the least amount of weight dropped, simply because of the way the motors are interfaced with the side plate. There wasn't a lot of wiggle room that we could really do with the left side plate, so we only dropped approximately 0.2 pounds on that. The right side plate we dropped more, once again, because of the interfacing with the rest of the climber, so that was 0.3 pounds. The drive rollers, this is where the weight really comes off of the climber, is because currently they're just solid pieces of polycarb, and that makes them incredibly heavy. And by hollowing them out, and especially since we have so many rollers, hollowing them out really drops the weight. So each of them is approximately 0.7 pounds lighter. Multiply that by 4, 2.8. But that's a lot of weight that our climber doesn't have to worry about, so that we can really increase our speed without increasing our power. And the same with the guide roller. So we managed to drop 5.5 pounds, which is a pretty significant amount since our climber itself is 33.7 pounds. It's a pretty substantial chunk that we managed to cut off.
Especially since a large amount of that weight is in the motors and the brakes.
Right. So we couldn't really do much with these 2 parts here. Keep costs low. We did this. We charge all the materials that and the manufacturing to the space elevator team budget. So we didn't really count this specifically to the labor costs that it would take me and Ryan to do. So the cost to the team this time was about $100 for the water jetting, which was about $45, and the polycarb, which was about $60, somewhere around there. So it was approximately $100 for the team to manufacture these pieces. Clamp time, we didn't have the ability to fully test this out, simply because we didn't have time or the ability at the moment to manufacture the rest of the side plates, so we couldn't create a final full assembly yet. So we couldn't actually test the clamp. But we kept the clamp design from the previous climber, this one right here, which is simply pieces of polycarb that are bolted into the side plates. And then these pieces are then bolted together. So it's a very simple interface. You just need a screw and put them together with the and things like that. So it works pretty quickly with this recursion, and it shouldn't really increase in time with our current version. The factor of safety, as Ryan discussed beforehand, we managed to keep the factor of safety in our requirement levels. For the Belay sidebars, 2.3, the sidebars themselves, 2.2, both rollers types were 2.1. The side plates, they have a much higher factor of safety, simply because we couldn't completely remove all the dead weight. So the left side plate has a FOS of 20, and the right one has an FOS of 17. Okay. The focus of this was, of course, to minimize the weight in order to speed it up. Cost really wasn't that important to us, because we'd rather have a working climber than we're willing to pay a little bit more money if it'll help our climber work better. And we wanted something simple, because if you make it too complex, the possibility for errors just really compounds. The manufacturing, as I said, we water jetted all the pieces out. We milled the holes, the same for the side plates. The rollers, come from long tube, we cut those on bandsaw, then we laid them out, because that is the most effective way for our rollers. The caps, they're essentially produced the same way. Assembly, everything is simply screwed together. There's not much complexity in how we do it. Since we milled the holes into it, we can just, with an Allen key, Allen wrench, just put everything in. This is our cost if we for like the labor rate for everything. And that would be for this would be a total of $13.43, which is a fair amount of money, but for a prototype of this type and the hours we put into it, I think it's completely reasonable. Future work, not everything was finished as you can see, but we do plan on finishing this up so that we have a more efficient climber. After all this, it'll just simply be assembled, and then we'll test it out the same way we have with this model. The weight drop is significant and will help us out a lot. It will definitely improve the performance. We definitely kept the factor of safety in a good level. We can continue this process by shaving off little bits here and there. We're not done. This process can definitely continue on and on, so we get a more finely tuned machine every time. Lessons learned. Do not trust random unified students to help you. We messed up our parts on the water jet because we were putting it on there in a sheet of polycarb and it had the plastic still on top. And we're like, oh, let's remove the plastic. And a fellow unified student was like, oh, no, leave it on. That way it doesn't splinter up and everything. I would leave it on. So we left it on and it ruined our water jetting. So that's why we don't have a completed climbers, because most of our pieces were destroyed in that. And if it can't go wrong, it will. We managed to ruin it about 4 times in one day. As I said, we can keep on doing this. Also, double checking all holes. That's how we messed up other parts of the climbers. We realized it wasn't in the spot it was supposed to be. As I said, peel the plastic off before water jetting. And we should have actually paused and checked the water jet more often. I think we did maybe like once, maybe glance at it, but not really. And with the sidebars, truss design was definitely not the way to go.
Thank you. Okay. Any questions? Anyone have some water? Carolyn?
Yes, take your coat.
Any questions? Jeff, do you have a question?
What's the banded material in the rollers?
So we added this a couple of days ago, basically to increase the friction of the rollers on the climber. We had knurled the rollers previously, but as you can see on the polycarb, we could not go in very far with the knurling. So, like, I mean, if you come up to it's a little bit heavy to pass around, but there's not very much friction here. So we added the rubber bands to attempt to increase that friction. That hasn't been tested yet. We're waiting to redo one of the gears before we do that. But.
And I might have missed that in the presentation, but what have you done to regulate the pressure between the rollers?
So we didn't address that in the presentation, like you said. Basically, the pressure between the rollers is regulated by, we have a bolt that we put through this through hole and then screws into here. And we have a small spring mechanism right up here with a few springy washers, basically. And we tighten down to some fixed amount that we haven't determined yet because we've gotten it to go up ribbon so far, but we're waiting to get one more gear finished, and then we can actually figure out what the optimal tightness is between the legs.
When the team ran the thing off the ribbon, there was a lot of slipping, and one of the trains were improperly machined. So we're remachining the gear train today, and then doing tests tomorrow.
I have a question. So you focused on the structural containment. If you had to sort of take the next line of attack on weight reduction and efficiency, the motors, if I remember correctly, those motors were chosen fairly quickly. Do you think they're going to be the right motors in the end? How heavy are they? Are they a substantial portion?
I would like to do a trade study on both the motors and the brakes. We chose the brakes largely, we did look around a little bit for the brakes, but they were largely chosen on cost rather than anything else. So, and actually when I was going through last night and calculating cost, or the weight, on the initial CAD model, or on the model we were doing our finite element on, I made sure to add all the materials on. But on the first one, I hadn't done that. So I checked the weight on this new one, it's 33 pounds. I checked on the other one, it's 23 pounds. realized that these guys did not have a mass, and part of the motor did not have a mass. So I'd say the brakes and motors together are probably about 15 pounds. So at least half of the full weight.
What's the motivation of having the brakes on there?
The purpose of the brakes is basically to be able to lock it in position on the rivet.
Also, we have to have a controlled descent, so we can't just have it free fall down the rivet.
Shorten the motors along with your gear ratio, will that not braking? You know, when you short the
We're not-
motors and improve that.
We're not allowed to apply power to the motors during.
If you just actually short the motors, you're going to create back EMF, which will actually counteract movement, and they will act as a brake if you just put a wire between the two terminals. That might work.
It's a good idea.
Any other questions?
We should test that. I'm sorry if you addressed this before I got here. Most of the conference was rollers and zigzag cross sections. The tension of the ribbon provides some of the reaction force. The ribbon and rollers, why did you choose kind of parallel? Is that so you can regulate it more easily?
Yeah, we were looking at that initially, and we decided that for the sake of not having to worry about the curvatures that would be necessary, and for the ease of clamping it on, it'd be a lot easier to just use linear than to have it snake through the rollers.
Okay, thank you.